Okay, now we're going to talk about latent factor approach. So far, we calculate the dissimilarity between the items or between the users directly, but we can use latent factor approach. So in this approach, we can project users and items in a continuous vector space. So in this slide, you can see that these users are here, and you can see these movies in the same space. Okay, so in this space we can actually see who is similar to whom. And also we can see the dissimilarity between the distance between these two, between the user and the item. So based on this distance in this latent space, then we can do whatever we want. Okay. And to project users and items in the continuous vector space, we can use many different algorithms, and one of them would be a singular vector decompositions. So when we have a matrix M, the M is a matrix of user and item. Okay, so when we have a user and the item matrix, then we can apply this SVD. Okay, then this is the U matrix, and this one is the V transpose matrix, and this one is the sigma matrix. Okay, then Alice can be represented in two-dimensional space, and Bob and Mary and Sue, and they will be in the two-dimensional space. And the Godfather and Die Hard and Star Wars, they are in the two-dimensional space. Okay, this is the vector and vector and vector, etc. Okay, then how can we use this latent space to predict the label, to predict the rate? Okay, then this rate estimate is based on this. Okay, this one is a bias term. Okay, then so we are interested in how much Alice like Batman. Okay, so then Alice and the sigma matrix and the Batman. So in the previous slide, so let's say item 5 is Batman, so this one is a question mark, so we want to know what kind of number would be in this cell. Okay, so this is empty cell, so we want to know that. So after this decomposition, then to estimate this rate, then we can multiply this vector and the matrix and vector. Then now we can get this number. Okay, so that means Alice would like Batman this much. Okay, and then we can apply the matrix factorization method, like non-negative matrix factorization or NMF. And given words and documents matrix X, then each cell indicates the frequency of the words I in the document J. So we just count how many times we have word ith word in the J's document. So all the numbers are positive here. That's why we could apply NMF. And when we apply NMF, then we can get W and H. And the W has topics. This one is one topic, and we have lots of topics here, or bases. And the H has topic loading. Okay, then this one is words, and this one is documents. So when we multiply W and H, then think about this one. So this one is a topic, and this one is a loading vector. Then this one says how much we will load this topic in that document. Okay, and This one is indicating how much we are loading this topic in the document. Okay, so we can decompose this matrix X so that we get W and H, and then in the W and H we have some meanings of the topics or the topic loadings. Okay. And we can train this NMF or matrix factorization method based on this MSE. Okay. So training step for R sub UI, user and items, non-rating of user U for item I, and we want to minimize this. Okay, so R is known and the P and Q are unknown, so we have to estimate the P and Q matrix. And in the R matrix, some cells are not known. Okay, some cells are not known here, and we want to estimate some specific cells here. So given known ratings, okay, some cells are known. Based on this information, we want to estimate the P and Q. So when we have a P and Q matrices, then we can estimate all the other empty cells. Okay, so these are known elements in this matrix. Then we want to estimate. We want to minimize these errors. So now after this training, then now we have matrix P and Q. Then we can estimate all the empty cells here. Okay, so to predict the rate for user X and item Y, then we can calculate this inner product between P and Q. Okay, so far we have been talking about explicit feedback. As an example, Netflix has a star ratings for movies and the TiVo, and we can provide explicit feedback to recommendation systems. But as I said at the beginning of this chapter, sometimes we have implicit feedback. Okay, so for purchase history or browsing history and search patterns. So based on these user activities, we can actually implement a recommendation system, even though in this activity we don't actually provide any feedback. Okay, so sometimes we click and then we just see the item and then that's it, and we didn't say anything about how much we like it or how much we hate it. We didn't say anything, but based on this click, the system can actually estimate how much the people like that item. So basically, when people click one specific item a lot, it means that it's hot. So people will like that, or at least people want to see that item. So we can display that item more frequently. Okay, for implicit feedback, if we want to use collaborative filtering, then this is one way to do that. So this part is just regularization, so ignore it for now. And this one is quite similar to the previous equation, but in the previous equation we didn't have this part. We had RUI minus P transpose Q, right? So we just changed the variable name, but basically the same things, okay? But in addition to this term, we have a C sub UI. That's it. And C sub UI puts some weight, right? So if it is a click, okay, then the P sub UI would be 1 or 0. Okay, so if it is 1 or 0, then we need a different weight for different items. So when the people click this item a lot, or when people click this item once, then still it is clicked, right? So it would be 1. Then the question is, if this estimation is not correct, then we need a different weight, because sometimes if this item is a hot item, then we have to be correct. And if this item is not that frequent, not that hot item, then even when we are not correct, then it's not that big a deal. Okay, so C sub ui will control that kind of weight. Let's say R sub ui is the number of clicks. Okay, then if alpha is 0.01, then if the item has just one click, then the CUI will be 1.01. But if the item was clicked like 100 times, then the COI will be 2. So it's twice. So between the 1 click and 100 clicks, then CUI, the difference between CUI is just twice. Okay. So based on this click information, then we can estimate how likely the user would click that item or not. Okay, so we can recommend which item should be displayed in the user's screen. Okay, so far we have been talking about the many recommendation algorithms. Okay, then first of all, we can discuss about the serendipity. So which way would be better? Do you want to recommend the popular items, or do you want to recommend unpopular items which users might like? So it's a serendipity. So which recommendation system would be better? It depends on the situation and applications. Okay. And another issue is that when we evaluate the recommendation systems, actually we have to check total sales numbers. That is the best evaluations. Okay, so when we evaluate a recommendation system based on the MSE or whatever, then even with these numbers, when the recommendation is really good with these numbers, but if it is not working in practice, then it doesn't matter, right? So we need this one as an evaluation. Okay. Likewise, we can check promotion of certain items or click-through rates or interactivity on platform and customer return rates. So actual improvement would be a good measurement to evaluate the system. But when we develop a recommendation system, then it's whole another story. So when we are in the middle of developing the system, then we cannot deploy the system in the actual system. Then what kind of alternative evaluation could be used to evaluate in the middle of developing process? Okay, so first one, laboratory studies. So in this case, we can control the experiments and we can simulate the situation, and then we can actually train and evaluate in the simulation. But the problem is, if this simulation is not correct, if there is a gap between this simulation and the actual system, then this solution is not the best solution. Okay, then next one is offline experiments. So it's based on the historical data. So we got the whole data from actual system. And then we can train the system based on the first 90% of the data, and then we can predict the last 10%. Okay, so if it is explicit, if there is explicit feedback, then we can predict the explicit feedback of the last 10% based on this system, right? Then we can evaluate our system. So prediction accuracy or coverage or something like this, or RMSE. So we can use this one to evaluate our system. So far, we talked about explicit feedback. So when there is explicit feedback, then we can try to estimate the feedback. But if it is implicit feedback, then there's no such a thing. So we cannot evaluate the recommended system based on the accuracy or RMSE, because the question is how many of the recommended items are clicked, okay, or how many clicks are on the recommended items. These two questions are important questions, and there's no way to evaluate these questions, because when we actually recommend some things in the user's screen, then there is a difference between these recommended items and not recommended items. If it is recommended, then the users would more likely click that item. Based on this recommendation, we actually change the display. And then we cannot actually predict something. There's no such a thing here. So it's completely different. So it's hard to evaluate, but we can calculate the precision and recall. Okay, and then based on this evaluation, then we can build up our recommended system. And then when we deploy, we can evaluate this system based on the total sales numbers or click-through rates and etc. Okay, this is it.